Hello friends, in this video I am going to discuss membrane potential. So what is membrane potential? Each and every cell in our body has excess of negative charges lined up inside the membrane, and that creates a negative potential inside the membrane, that is called membrane potential. So any potential that would be in the inner aspect of the membrane, and every cell has its own membrane potential, but the value differs. Let's see the value one by one. For RBC or epithelial cells, the membrane potential is -8 to -20 millivolts, and for smooth muscle cell, the membrane potential is -35 to -45 millivolts. For SA node, the value is -55 to -65 millivolts, and for nerve -70 millivolts, and for skeletal muscle or Purkinje fibers in our heart -90 millivolts. So this is the range from less negative to high negative for the skeletal muscles. So these are the values of the membrane potential inside the membrane, and all these cells are surrounded by extracellular fluid whose potential is taken to be 0. Whatever the value inside the membrane, whether it's -8 or -70 or -90, the outside extracellular fluid potential is taken to be 0. Let's take the example for skeletal muscle. Its transmembrane potential would be 90 millivolts. But there is one exception, and here is the question: which of the following has the highest electrical gradient transmembrane potential? And the options were RBC or skeletal muscle or rods in the retina or hair cells in the cochlea. And the answer is hair cells in the cochlea. Let's see why. So hair cells in cochlea are the receptor cells for hearing and equilibrium. And our hair cells are surrounded by endolymph. Endolymph is the extracellular fluid, but it resembles more of intracellular fluid because it has high potassium concentration. Because of the high potassium concentration, its potential, endocochlear potential, is plus 80 millivolts instead of 0. For all other cells, their extracellular fluid potential is taken to be 0, but only for hair cells in the cochlea, because of the high potassium concentration, the endocochlear potential is plus 80, and inside is -70 millivolts. So the transmembrane potential for hair cells in cochlea is 150 millivolts, which is the highest in our body. So hair cells are the most excitable cells in the body. Now for two tissues, we will use the term resting membrane potential. Those are the excitable cells, and they are nerve and muscle. For nerve, the resting membrane potential is -70 millivolts, and for muscle, mostly of skeletal muscle, it's -90 millivolts. These cells are excitable, and the membrane potential becomes positive temporarily and then becomes negative. And why there is membrane excitation and what is the purpose? Let's see. The membrane excitation is in the form of signal transmission. When a membrane excites, signals are being transmitted from a nerve to another nerve or from a nerve to muscle. So the muscles will electrically excite, and as a result, the muscles will contract. So what is the purpose? Muscle contraction. Signals are being transmitted and the muscles will contract. Let's see the origin of resting membrane potential. The resting membrane potential is 90 millivolts. But the question is how the value comes. For this, you have to understand equilibrium potential for an individual ion. Let's take sodium. Sodium has its concentration gradient of 141 milliequivalent per liter on the outside, and inside it's 40 milligrams per liter. Due to its concentration gradient, ions will move from highest to the lowest, right? It will move from outside to inside. As sodium starts moving in, it carries a lot of positive charges lined up inside. Let's assume all other ions are not moving, only sodium will be moving. So sodium will be moving from outside to inside due to its concentration gradient, and it carries a lot of positive charges, and positive charges are lined up inside. It creates the electrical gradient. So two things will happen. One, the concentration gradient will become narrow, and it carries the positive charges, right? So the charge will be plus for sodium. So to know the equilibrium potential for an ion, we are going to use the Nernst equation. The electromotive force is equal to plus or minus 61 into log of C1 upon C2. So for equilibrium potential of an ion, the equation we apply here is the Nernst equation, and let's apply for sodium. For sodium, the charge is plus because it is a cation and it carries lot of positive charges inside of the membrane. So the charge would be positive, and log of it would be plus 61 into log of 10. Log of 10 is 1. So the answer is plus 61 millivolts. So this is the equilibrium potential for sodium. When the membrane potential is plus 61 millivolts, the sodium will be in equilibrium and there will be no net movement of sodium. Let's see for potassium. For potassium, the concentration gradient on inside is 145 milligrams per liter and outside it's 4 milligrams per liter. So the ions will move from the highest to the lowest, right? So it will move outside due to its concentration gradient, and it will create the positive charges lined up on the outside, creating the electrical gradient. So when we apply this Nernst equation for potassium, equilibrium potential for potassium would be minus 61 into log of 145 divided by 4. The equilibrium potential for potassium would be minus 94 millivolts. Why here the charge is minus? Because potassium is a cation, and when it moves from inside to outside, it carries the positive charges outside and left behind the negative charges inside. So the charge will be negative, and its equilibrium potential is minus 94 millivolts. And our resting membrane potential is minus 90 millivolts. Here you can see the resting membrane potential and equilibrium potential for potassium is almost same, right? It's almost near. And when a sodium equilibrates, its value is plus 61 millivolts, and when potassium moves and equilibrates, its value is minus 94 millivolts, and the RMP, resting membrane potential, is minus 90 millivolts. Here, potassium is the greatest contributor for the development of RMP because potassium moves from inside to outside, and potassium is much more permeable, and membrane is much more permeable to potassium than compared to sodium. So like 50 to 60 times potassium is more permeable than sodium. So potassium is the greatest contributor for the development of resting membrane potential. So the values are almost near normal, near closest. So the so potassium is the greatest contributor, and you have to know equilibrium potential for chloride. It's minus 89 millivolts when you calculate in Nernst equation. And this value of chloride is also closest to RMP, right? This value of minus 89 is closest to resting membrane potential, but potassium is the greatest contributor. In the sense, chloride hardly moves and it almost remains in the equilibrium. So the chloride hardly moves because it's in the outside, right? Chloride is in the outside, it moves from outside to inside, it hardly moves and remains in equilibrium most of the time. So the resting membrane potential is minus 90 millivolts. Thank you.